Just another comment, maybe it's related to what I also said yesterday. So today the discussion is led by Shlomo. And then, so you will get him, and then the afternoon is all on him. Okay, and then tomorrow there is no planned lecture for the afternoon, but the discussion is here. So we will decide later on who will lead it, but the discussion is going to happen. Okay, so let's continue what we did yesterday. So the idea, I will just summarize a bit what I discussed yesterday, and then we will continue more or less on the same topic. So yesterday, what I discussed is essentially how can we map the singularities of the correlator with the CFT data, essentially. In particular, we saw that if we have an exchange on the direct channel of the identity operator, this is mapped to these operators that at large spin. And those objects, if you remember, those are just a double particle. So the dimension, as we saw yesterday at leading order, is twice the dimension of this object, plus 2n plus L. And as we discussed already yesterday, this operator is always there. So this is the unit operator. This operator is always there in the OP of identical operators. So remember that in order to get this mapping, we use mostly the fact that our correlator is crossing symmetric. And so this is always guaranteed in this kind of in the correlator of identical operator. And then we showed then if this is the case, so when we have a unit operator in one channel, this ensures that there is a family of operator whose dimension approaches this one here for very large spin. So in particular, we got two information. One about the existence of this class of operator, and the second thing is the necessity of large spin. Because if you remember, in order to reproduce the divergence on one side, we had to have this, in order to have the divergence in order to reproduce the divergence on the left-hand side, we had to have this class of operators. So in particular, the idea is this one that I wrote at the beginning, that the singularities of the correlator, they constrain the CFT data. That's the story. So we don't need to know the full. So if you remember on the first part of the class yesterday, we saw that if we have the complete expression of the GUV by doing the conformal block decomposition, so if we knew all the full correlator, we could, by using the conformal block decomposition, we could compute delta, L, and the 3-point function squared. But by what we said in the second part, if we are interested in understanding this object for large spin, it's enough to know the singularity of the correlator. We don't need to know all of it. And in particular here, one of the singularity, the leading singularity, is controlled by the fact that we have the unit operator, which is always present. So we didn't need to input any further information. Today, we are going to see a technique which is called inversion formula, which will make this much more precise in the sense that yesterday I gave you a flavor, a taste on how this works, and today we are going to see a precise statement about how to relate the singularity of the correlator in one channel to the CFT data. And in particular, we will see a relation which puts then that in a solid footing. Questions about what I said yesterday, something that you were completely lost because it was late in the afternoon, and if you have some pressing question, I'm happy to address it now. Otherwise, we can also discuss it during the discussion session. But that's more or less what I wanted to say. Okay, so please try to do it, the steps that I did yesterday on the board, try to do it by yourself because it helps a bit in getting an idea of what's going on. So the way in which I'm going to present the inversion formula is by starting with the general idea, then I will present the result, and then we will briefly discuss how to get to the result. But I won't prove it for you, the full equation, because it will be a pain, and that's not the objective of this course. Okay, so the idea, what we would like the question that we want to answer. So this machinery inversion formula or integral, this has been put forth by Simone Caron-Watt a few years ago, not many, I think 2016 or 17. So the idea is this one. Imagine the rough idea is that we have our correlator. So if we say we have this kind of decomposition, we know, again, I will be sticking to 4 dimensions, but just for convenience. You can use that in any kind of space. So this is the space-time dimension. And the idea is that imagine that we have some expansion of this form. So we know those functions. And indeed, if you assume some properties for the function on the left, it's not that this coefficient can be randomic. So if we have a basis of function and we impose some properties on this function that we need to expand, the coefficient of this expansion cannot be any number that we think of. So already putting very little assumption on the left-hand side will give us some constraint on this function here. So that's the whole idea. Let's try to understand what are the properties of this function on the left-hand side, which is our 4-point correlator, in order to find constraints on this object here. That's a bit the idea. Let's start with a much simpler problem. So let's think about general complex analysis. So imagine that we have a function, f of x, and we are going to write this in a power series. And this will be some coefficients, f of j, x to the j. And then we will assume that there are these properties. So f of x is analytic in the whole complex plane, except for the branch cuts at real x greater than 1. And then let's assume that f is bounded in this way. This is like a simpler at least problem. Now we can use in this problem, and again, we have these two relations. These two conditions are very mild condition on the function f. So this is like a toy model for this one here, because here we are a function of two variables. Here we have two sums and so on. So this is really a toy model of that, but essentially it's the same. So we are on the right hand side, we have an expansion around this variable x, and here we are putting some mild assumption on the function on the left hand side, and we would like to understand how and if we can find this coefficient f of j. Now the f of j in this way are pretty simple. We can use Cauchy theorem to evaluate them, and Cauchy theorem tells us this. It tells us that we can write the f of j as 1 over 2 pi I contour integral of dx over x to the minus j f of x. Now, what we can do, we know that f of x over x goes to 0 as x goes to infinity, so we can deform the contour, and so we can use the condition 2 to deform, so, and deform the contour to be able to write f of j in this way. 1 over 2 pi integral between 1 and infinity, because again we said that there are branch cuts, so we use the condition 2 and we deform the contour by assuming 1 in this way, so we will get dx over x to the minus j, and then we will get the discontinuity of the function f of x, where the discontinuity is defined as minus I f of x at 1 plus I 0 minus f of x 1 minus I 0. This is just the usual trick that one does. Essentially, there is the branch cut, so we need to go around the branch cut, and then we can deform the contour, because f of x over x there is bounded. So here, this the case when we go to infinity. So essentially, we can just replace this contour integral by the line integral here. This is similar to what we do when we compute the principal value, essentially. Now, what can we learn? We can learn from here that the f of j's are analytic in general. So if you look at this equation here, for real of j greater or equal than 1, and they are fully determined by the imaginary part of f of x, because of they are completely expressed in terms of the discontinuity of the function.
Sorry, how is this discontinuity defined? That I is minus I is multiplying the whole thing.
Yes. Sorry, yes.
And it's that's 1 plus I times 1.
0, so you are going around x equal 1, so you are computing it. So you know that there is a branch cut, and you have to go around this branch cut, essentially.
I'm sorry, how do we do this? Because isn't there a sum over j?
No, this is a single f of j. Yeah, yes. So essentially, what you do in general to compute that is like you use the contour integral to determine one of them, like this relation here is pretty simple, because in order to pick the f of j, you need to compute the residue, essentially, of that. And this is what you would do. And then, due to the fact that f of x is analytic, except for the branch cut, we need to go around the branch cut. So essentially, there is a full machinery. I don't know if for people who are familiar with that, this is very similar to what happens when you have the Froissart, similar to what happens. I won't enter much into details here, but to what happens in Froissart, Gribaud, formula. In that case, instead of having this x of j, you have polynomials. So for instance, when you expand your function in spherical harmonics, you can do the same thing here. So if you expand in spherical harmonics, then you can find the coefficient of the expansion using this technique. So it's essentially equivalent. Now the question is, can we do, so this is a very simple relation, because this is a function of a one variable, complex variable, and the idea is, can we use, so notice that what we achieved is that we get, let me maybe write it for you here, in this very simple example, we got that we are able to write our coefficients, so and first of all, we notice that they are analytic in J. And in addition, those are related, so those are fully determined by the discontinuity of f of x. Sorry. And in particular, the discontinuity is fully determined due to the fact that we have this I here by the imaginary part of the function. Now the question is, can we do the same for CFTs? So the idea is to go back to the main relation there. Now, this is much more complicated. First of all, because that relation up there, as we discussed yesterday and the previous time, this is written in Euclidean. So now we need to move to Lorentzian in order to be able to apply a technique similar to that, because we need to think about the full space. And second of all, here we have two variables. So we need to go from one variable to two variables, and we need to go from the Euclidean to Lorentzian. So the first thing is so the first step would be to see if there is an Euclidean version of this relation here. So there is a Euclidean way to invert the OP. And then we need to understand if we can go from the Euclidean to the Lorentzian. And since we are discussing about that, indeed, the answer is yes, there is. So the first thing that I'm going to do, I will show you how the relation works, and then we will go backwards. Before maybe doing that, so first of all, do you have questions on that? It is clear the logic that we are going to pursue? Okay, so first I will write for you the result. So I will write point 2, and then we will try to understand how in principle we can get it. So okay. So the relation is this one here. I will again, we are in 4 dimensions. Okay, now let me try to explain what I'm talking about. So this K is very simple. It is just some ratio of gamma functions. Gamma of 2 alpha minus 1, gamma of 2 alpha. And then this CT is related to this function. I will discuss in a second. And first I will define everything. So d disk is the Euclidean G minus 1/2 G z bar when we go around Okay, so now I've written it. I saw yesterday there was the stick. Okay, good. Okay, let's look at this relation here. First of all, for the moment we don't know what C is. Let's say something. It's a function. We will discuss in a second what it is. So T means that we are in the crossed channel. So T and U are, one is the direct channel, one is the cross channel. So remember again, no, I erased, but we have the picture. So we have to look again to this one. So let's say this is channel T and this is channel U, just to put it this way. We will see what exactly this means, but we have this object here, and we managed to write this object as an integral, so a double integral, both of them are between 0 and 1, of some kernel. This kernel is related to the usual conformal blocks, but notice that we are swapping the indices, so this is not a typo. Here, where we used to have the dimension, we have the spin with this shift, and here we have where we used to have the spin, we have the dimension. And then there is some other bit, and then very importantly, we have the double discontinuity. So remember, in this simple example, here we got the discontinuity. We started with a single variable function. We got into a single discontinuity around our branch cut. Here we have a double discontinuity because we have a 2-variable function, and the double discontinuity is defined in this way. So we take our GUV in the Euclidean, and then we subtract the analytic continuation around z bar going to 1. Remember, z bar going to 1 is the limit of v going to 0 that we discussed yesterday. So yesterday we saw that when we were taking the v going to 0 limit, we had the divergence that we needed to take into account. So notice that here we are thinking about v going to 0 because we are in the T channel, so in this channel here. So remember, yesterday we were doing u equal to 0 because we were in the cross channel. So here we are in this channel here. And then we need to take the v going to 0 limit. And it is clear that this discontinuity is determined by the singularities around this point. So what we managed to do, we managed to find this function is completely fixed. So there is no problem with this. This is just a function that we know is the usual block. So inside this object, everything is known but this function. So this is our unknown. And this is indeed what we wanted to compute. So this is fully determined by the, let me remove this. This is fully determined by the singularities around z bar going to 1 or v going to 0, which is the same thing. And now this gives, so we need to compute this integral, and then we will find this object from which we can build, sorry, L delta here. Delta L, from which we can find this function here. Now let's try to understand what is this function. Okay, so here we have achieved at least a part of our goal because we generalized this relation here. So we found our coefficient, which now I call them C. Let's see how those are related to the A and to the delta, which is what we wanted to find. And then we managed to rewrite it as an integral, the same thing here. So here we have z and z bar. Essentially what we are doing, we are integrating on that plane that I showed you yesterday. Remember, yesterday I wrote this diamond here. We are integrating in exactly this region here in the z bar coordinates. And then here we have our kernel. This is completely determined. And our unknown is a discontinuity of a function. This is double because, again, our function is a two-variable function. That's more or less the idea. Now let's try to understand what is this C. Okay, I will write it here. So this is, they are called spectral functions. And they are essentially so this function, C of delta and L, has poles at the dimension of the exchanged operator delta k, which means this. So when delta goes to delta k, this function behaves in this way. So it has poles when delta is equal to delta k, with residue A of delta k L. So where the A is exactly that A up there. So this C encodes both the OP coefficient and the spectrum, because by looking at the pole structure of this C, we will get the dimension, and by looking at the residue of the pole, we will get the 3-point function squared. So this is why it is called the spectral function, because it contains both the spectrum, so you see here, so this contains both the spectrum and the OP coefficients. And then also, similarly to the way in which we saw this object here, so we saw that this was real, this was analytic for the real j greater than 1. The thing up there is also completely analytic. So the only non-analytic thing is this piece here, but other than that, the function is fully analytic. And actually, so except this object, this function is fully analytic. In L, for L greater or equal than 1. This is a bit subtle to understand why for L equal to 0 is not analytic, but we won't go into these details. Now let's try to understand again the full logic here. So we managed to find a relation. Do you have questions on that before I rediscuss it? Is it a bit clear what is the logic behind that relation here? Yes? Yes, so we have singularities. We have a singularity pattern around z bar equal to 1. In particular, we have either branch cuts or poles in the z bar equal to 1. Because remember, yesterday also we saw that we have something like 1 over v to some power, for instance. So this will produce, when we go to the Lorentzian signature, object like 1 minus z, 1 minus z bar to some power, which are indeed singular where z bar goes to 1. These kind of objects, or we can have, for instance, log of 1 minus z, 1 minus z bar to some power, for instance. This object have singularities when z bar is equal to 1. In order to capture in order to do the same logic that we would do in two variables, so we have now z and z bar, and the singularity structure of z bar is controlled by z bar equal to 1. Now we can build, we can show, it is possible to show, this formula is proven, that the coefficient of this expansion up there, related through that relation there, are determined only by this discontinuity. Now this is not a discontinuity in z and in z bar, is a double discontinuity, meaning that you are going around clockwise and anti-clockwise around the analytic continuation of z bar equal to 1. So you go around, you add the plus I and minus I to go around the z bar equal to 1. And this is what it means, this circle here. So you go on one hand and on the other hand, and then you subtract the function that you have. For instance, you have this object, you have to put 1 over 1 minus z, 1 minus z bar to some power minus the two analytic continuations. Okay, is this clearer now? Notice that this is not a discontinuity in z and a discontinuity in z bar, which maybe is what one would have guessed for a two-variable function. This is not the case. And indeed, instead, there is the discontinuity around the two way of analytically continuing around z bar going to 1. So this is reminiscent to what we said yesterday. So yesterday we saw that in order to reconstruct, by assuming crossing symmetry, in order to reconstruct, on one hand, the large spin expansion of let's do it the other way, sorry. So in order to reproduce our singularity in one channel, we had to assume that we had some operator which would behave in a certain way with the spin. So here we are essentially saying the same. In particular, we see that our singularity structure, which is all encoded here, fully determines how the C needs to behave. And in particular, due to the fact that this object is fully analytic in the spin, it tells us that this has to be true not only for large spin, that is what we said yesterday, but it has to be true also at any order in perturbation theory in the spin, and even for finite spin. So yesterday we saw that in order to reproduce the singularity, we needed to have the spin being infinite. Today we are seeing that actually we can do much more than that. We can use this matching of singularities, and this would fix for us both the poles of this function C and the residues, also at finite spin, except for spin equals 0. Okay? Questions on that, please? So, well, it's exactly the same procedure, but you have to do the other channel, essentially. Yes. Now, let's try to think a bit to what we did yesterday, and try to rethink about it. So, first of all, let me give you, look, let me erase up there while you think about it. So let's remember the example that we did yesterday. So yesterday, generalized the free field. Now, in the yesterday generalized free field, we had that GUV was equal to 1 plus u to the delta phi plus u over v to the delta phi. Do you remember that? If you don't remember, you can look it up. So in particular, this was this object here. This is this object here. And this is this object here. Okay? Then you can figure it out. Now, what we saw yesterday, we saw that essentially the fact that we have this one here already fixes for us the fact that in the cross channel we have this object, because remember that so if we are looking to the cross of 1, we are saying that our GVU needs to contain, this u over v to the delta phi needs to be 1. This means that GVU has a v over u to the delta phi. Okay, is it clear what I'm doing here? I want to understand what is the crossing symmetric term related to the 1. So if in the GUV I have the identity, to what it corresponds to in the crossed channel. So by assuming that I have a 1 in our GUV, to what this is mapped to in the GVU variables. So this is v over u to the delta phi, through that, which means that the GUV needs to contain a u over v to the delta phi. Clear the logic? So I have a 1 in the direct channel. This means that I need to have a v over u to the delta phi in the crossed channel, and then mapped back in the GUV, this is u over v to the delta phi. And if we see it, in fact, we have it. We have a u over v to the delta phi, as we would have expected by this convoluted way of thinking. And actually, you can easily see from what we said that the only piece which has a double discontinuity which is different from 0, actually which has a singularity in the z bar going to 1, which part has a piece which is singular for z bar going to 1 in this whole expression? The u over v to the delta phi. Because this piece has a z bar over 1 minus c bar to some power. So this is the only bit which has a singularity around z bar going to 1, which is precisely what we saw yesterday. Yesterday we saw that by having a 1 in our direct channel, we needed to have infinitely many operator with infinite spin. Sorry, we need to have operators with infinite spin of the form that we discussed. And actually, we saw here that this is exactly the same, because if we know that if we have a 1, from the 1 we can reconstruct the fact that that we have this object here. Now, this object here has exactly this singularity in the z bar going to 1 variable. This means that the 1, which in the cross channel is a u over v to the delta phi, completely determines this object here. Now, I tell you this, and then you can try to do the exercise by yourself. So the double discontinuity of 1 minus z bar over z bar to a power p, this is 1 minus z bar over z bar to the power p twice sine square of pi p. Now, with this piece of information, you can try to compute what we computed yesterday using that relation upstairs. You don't need to know the exact answer. You can do it both ways. To start with, you can take this expression, take the double discontinuity, find that the only bit that you need is something related to that object there, and then you need to compute the C delta L, and in particular you will see that this C delta L, this integral is not a simple integral to do. I mean, I'm not saying that what I'm saying is simple or simply done. I'm saying that that's the way to do it. You see already that this double discontinuity has a sine square of pi p, which is already inside an integral, not the best thing that you want to see, because it's oscillating, and this is a sine square, so it just gives some zeros inside this full expression. There are tons of gamma functions. Then we have an hypergeometric function up there. Remember, the blocks are not the simplest thing in the world. So I'm not saying that this procedure is simple. I'm saying that there is a way, a closed form way, in which you use the double discontinuity, which is not even horrible. I mean, it's something like that in this particular case. The nice thing is that, see, here we have 3 terms, and 2 of them don't contribute. There is only one which contributes. So that's the most impressive thing that we are going to say today, that we don't need the CFT data in our correlator. We can forget about them. We can use that relation upstairs and find both A's and delta only by using that. Remember, yesterday I showed you that if you have this, you can expand around small z and small z bar, and then you can compute order by order. I don't know, surely you didn't have time to do it, but when you will have some time to do, you can try to do that way. This is way simpler, but you need to know the full information, the full 4-point correlator. So this is just a way of expanding it. What we are going to do today, this is much, much more strong. We don't need the full correlator. The CFT data, meaning the A, delta L, and the delta are completely determined for spin greater than 1, are completely determined by knowing this piece here. So you can, I think, appreciate the big difference. So now we are talking about a very simple, like some generalized free field case, but this works also for horrible expressions. Yes? Oh, indeed. Okay, that's the second question that we want to understand. So how do we use this object? How do we know the structure of the singularity? Here, if you have any other, so this was the thing that I would like to bring on for the next hour. If you have other questions relating to this, ask now about something that I might erase, for instance. Or some more generic question about the philosophy of this. Okay, then I will erase and we will discuss exactly that question, because now to go to the answer to this question, the idea is clear. We have a relation between the Cs and the discontinuity, but okay, how do we know the discontinuity? How can we fix the discontinuity? Because otherwise we are going like in a loophole. We will see from now to the end of these classes how to find the discontinuity, essentially, in order to be able to find the spectrum only knowing the discontinuity. And we will do that in particular for large N CFTs. Okay, but first we will start with this example again to see how we could have found the double discontinuity, and then we will go further. While I erase, you can, again, think about some question and ask them. So this is somehow, let me maybe say that which can be helpful. So when you compute your, I don't know, quantum field theory diagrams, so you are computing some QED diagram, and you want to compute the anomalous dimension of some scattering process. You don't require to know the full scattering problem, like you don't need to know the full function. It's enough that you look to the logarithmic part. And then you can read off the anomalous dimension. You don't need to compute the full piece. It's enough that you look to the piece in front of the singularity of the logarithm. This is exactly the same. So in order to find, this is much more because we have more symmetries, but the idea is the same. We don't need to know the full function. We just need to compute the singularities. So this is more or less the idea. In order to find the dimensions and the OP coefficient, we don't need to know the full function. It's enough that we know our singularities. This is related to exactly the same logic. There, you don't need to know the full function. It's enough to know the logarithmic part. And here is exactly, I mean, it's similar in spirit. I will erase this. Okay, I will leave that up there so that we'll keep having it. So how do we find the double discontinuity? So the way to find the double discontinuity, or the way to think about the double discontinuity, again, remember that there are very few things which can produce a singularity, or whatever is a power, so V to any positive power does not have a double discontinuity. So this is, we don't care about it. We care about 1 over v, 2 powers, so negative powers have double discontinuity for z bar going to 1. Then something else is logarithms. So this will produce double discontinuities. Then half integer powers will produce discontinuities. So we need to look at these terms here. Those are more or less, then we will do step by step. But let's look at these objects. The first thing that we can think of is 2 objects. The first thing is, again, crossing symmetry. The second thing is the OP decomposition. Yes? Yes.
So you could have v to the some positive power.
Yeah, sorry, here I mean integer. Sorry, indeed. V to any half integer as a double discontinuity, and also all powers or combination of those. I mean, if you have v to some positive power, integer power, you don't have it. Okay, so now we know these 2 facts. Let's try to think how we can use it to find some of this behavior here. Again, this just means the usual story. And now let's try to think about the OP decomposition. So the OP decomposition has this structure. Now, if we have an operator, so we can see from here, no? Like if we have an operator, for instance, which has dimension 2 and spin 0, let's assume that. Let's assume that I'm telling you I have an operator which has spin delta equal to 2 and spin 0. This means that inside this decomposition, we will have some a to 0, u to the 2 minus 0 over 2, which is 1, g tilde to 0 uv. Now, plus dot dot dot, which are all the other operators. I'm just taking this operator here. Now let's look to what happens using crossing. So if we have this kind of term, in the cross channel, we need to have, so G VU will be G UV times V over U to the delta phi, which means this object, so A to 0, U to the U, G tilde to 0, UV, times V over U to the delta phi. I did very simple algebra. Let's do it here. So G VU is equal to A to 0, U to 1 minus delta phi G tilde 2 0 UV V to the delta phi. Okay? Plus dot dot dot, whatever. Let's focus only to this operator here. Now let's put it back in the GUV. This is A to 0, U to the delta phi, V to the 1 minus delta phi, G to 0, VU. This means that GUV needs to contain this object here, because it contains this object. And now you see that you discovered something interesting. So, when z bar goes to 1, depending on what delta phi is, already tells us that in principle this object can have a double discontinuity. And the double discontinuity is completely fixed by this object, which is the block and the 3-point function of the operator that we know it existed. So by having one operator, we already know that due to the fact that our function is crossing symmetric, there is another piece inside our correlator, which may or may not, depending on the value of delta phi, has a double discontinuity. So that's the logic. So let's assume that we know something we should know it, and the fact that we have one term in the direct channel tells us that through crossing we have another term which might have a discontinuity in the z bar going to 1. This is what I did before for the 1, no? When we did the identity operator. If you put a 1 here, that's exactly the same. You have the discontinuity that we saw, the v to the minus delta phi. Okay? Yes, or it can be bigger than 1, then it's negative. So if delta phi is 4, it's enough 2, greater than 1. In general, I'm just thinking a bit about the logic. Another information, for instance, imagine any CFT should have a stress tensor. So this we know, and actually even more, if there is a stress tensor, we also know generically the 3-point function, because it's something that is generically protected. I mean, if we are thinking about it's conserved, let's say. Then in that particular case, we even know more, because we know this piece, we know the block because it's known, and we know even the 3-point function. So that is even more than that. And that piece is the stress energy tensor as dimension d minus 2. So this will have d minus 2, which is the spin over 2. Sorry, d. It has d minus 2 over 2. So we will have a term which is v to the d minus 2 over 2 minus delta phi in general, due to the fact that we have the stress tensor. That's the reasoning behind this. So as soon as we know something about our OP decomposition, which can be knowing one operator, we can do this machinery and find the C delta L, and meaning the A and the deltas. For instance, this procedure has been done for the Ising model, and one could see that indeed one would get with the accuracy the operators that you have. There indeed it's hard, because you know this object and the dimension only for the first few operators, so you don't reconstruct the full pattern of the full discontinuity. So this is only one bit, because then there are dot dot dot, and all these dot 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 have a U power growing, which means that by crossing they will have a full tower of this, and indeed if you know the full spectrum, indeed you reconstruct the full spectrum. But I'm saying that already if you know a tiny bit, you already will know something about it. This might not be entirely the double discontinuity of the full correlator. This is part of the double discontinuity of the correlator. Because indeed, I'm saying if there is only this operator, which that's not the case in general. I mean, those are very special theory. But what we are going to do in the remaining half an hour today and in the full lectures is to study, for instance, large N theories. In large N theories, we can reconstruct fully the double discontinuity up to one loop order, only with this reasoning and tree-level data. So that's the plan. That's what we are going to do. We are taking an example, which is a kind of very broad example, and through that example, we are going to work out the C delta L for essentially all our operators. That's the plan. But please ask questions if you have at this point. Yes?
So, if is that you know that there is an operator with delta equals to 2, let's say, which is, sorry, delta equals to d minus 2 and spin equals to 2, which is stress tensor.
Sorry, I didn't hear the last part.
We know that there is an operator which has spin 2 and delta equals to d minus 2, which is the stress tensor. And from that, what do we compute using this, using the singularity? Do we compute A 2 comma?
No, so let's assume that there is an operator G UV. Let's assume we only have the stress tensor, only stress tensor. Tensor, which means delta d and spin 2. So this means that we have A d comma 2 u to the d minus 2 over 2 g tilde d comma 2 uv. Okay? Now we use crossing. Crossing tells us this, which tells us that GVU should be V over U to the delta phi GUV, which means V over U to the delta phi times A d comma 2 U to the d minus 2 over 2 G tilde d comma 2 UV. Now we remove this from here and we write it minus delta phi here, okay? And now this means that the GUV needs to contain a term which is u to the delta phi a d comma 2 v to the d minus 2 over 2 minus delta phi g tilde d2 vu, okay? Now, assuming that generically for the stress tensor, we also have a conserved stress tensor, which sometimes tell us also how the 3-point function of two operators with the stress tensor behave. So in principle, this should be proportional to the A, this square is proportional to this object here. So this would allow from kinematical observation to determine this object. This, when delta phi is greater than d minus 2 over 2, gives us a power law divergence, and this will tell part of the double discontinuity of our correlator. This is what I wanted to say. But this won't give us a d comma 2. This is an input. And we would compute some C delta L related to it. This gives us a piece of the double discontinuity. No, because this will give a redundant information, because this A will be on the right-hand side too. This will be inside the double discontinuity, the coefficient inside. Now, if we only have the stress tensor, which we will see in a second, that's not possible to have only the stress tensor, but let's assume, let's forget about physics. We have only the stress tensor. This would mean that this is the only double discontinuity that our correlator can have, because there is nothing else. Then we could find all the C delta L. In particular, we could find if there are classes. I mean, you already actually see by yourself that this is not consistent on having only the stress tensor, because this would fix for us fully the double discontinuity, but the double discontinuity, which is different from 0, would tell us that we need operators which have infinitely high spin, and we don't have it. So only the stress tensor in a theory is not consistent with our object. Actually, this is a nice example to see that. Any finite, so if we have a set of operators that produces a double discontinuity different from 0, tells us that we need to have operators which have arbitrary high spin in general. And only having the stress tensor wouldn't work. More questions on this part before we go to large N, which is a completely different chapter. It's an application of this to a different context. It is clear the logic, more or less. If it's not clear, ask also silly questions, whatever. I mean, it's important that you get a bit the idea, otherwise it's very hard then to follow the remaining part.
Do you mind repeating?
Sorry?
Do you mind repeating what the logic is? Maybe a quick summary.
Indeed, perfect, yes. So let's try to get to the question that we wanted to ask. So the question that we want to ask is this one. We have our 4-point correlator, and we know two information about this 4-point correlator. The first information that we know is that this function needs to be crossing symmetric, which means that GUV is equal to U over V to the delta phi. This comes from a 4-point function of this form, where the operator has dimension delta phi, times GVU. This is the information that we know about our function. The second information that we know about our function is that it can be, since it comes from a 4-point function, it can be decomposed using the OP decomposition, which tells us that the GUV can be written as a sum over all the possible dimension and spin times the 3-point function of the conformal block associated to that operator here. Those are the two information that we know about our functions, GUV. Now, the question is, on a general ground, what's the minimum input that I need to know of G? So what is the minimum set of information on G to be able to determine delta L and A delta L? That's the question that we want to ask. So is it really true that we need the full GUV inside this decomposition? But this we know. None, because those are the conformal blocks that are fixed. Those are kinematical piece of information. So those are not important. This we know. Do we really need to know the whole correlator in order to be able to find delta L and the A's, or it's enough to know part of it in order to reconstruct it? Due to the fact that we have these two gigantic pieces of information that we have. That's the question. The answer to this question is no, we don't need to know, sorry, what's the minimum set is the double discontinuity. So we don't need to compute or to know the full answer. We don't need to know the full G. It's enough to know the double discontinuity of GUV. So this is, the answer is is we need to know only the double discontinuity of the G, which means the singularity pattern for Z bar going to 1 or V going to 0. If we know this bit of information of our function, then we can reconstruct by using this relation here both the A's and the delta and L. That's the summary of this story. Now there is an extra bit, which was what we discussed in the last part, is, okay, this is fine, but now can we make it more explicit? How do we control the singularity of this? How can we control the double discontinuity of this function? How can we fix it a bit? And maybe I will redo the example of the unit operator, which is what we did yesterday before going on, because then I can take it as a bridge to go to the other part of the class. So let's assume, as an example, let's assume that we know, and this we always know, that in the OP of our theory there is the identity operator. So phi has the identity operator in it plus some other stuff that we don't know. Okay? So if there is the identity operator, using statement 2, we know that our correlator contains a 1 plus ... because the delta of this is 0 and the A 0, 0 is equal to 1. And the block, is equal to 1. Clear so far? This is not even an assumption. We always know that there is a 1. Now we use 1, crossing symmetry. So if let's assume that we don't have the ... Let's see what's the crossing symmetric counterpart of 1. Let's take that relation up there, which tells us that GUV is U over V to the delta phi GVU. And if this is 1, we have 1 equal to U over V to the delta phi GVU. Let's find the GVU. This tells us that GVU is equal to V over U to the delta phi. Thus, this means that our GUV needs to contain, in addition to 1, another piece, which is U over V to the delta phi. Okay, this is by assuming 2 plus 1. Clear so far? So, crossing symmetry is telling us that our correlator GUV needs to have 1 plus U over V to the delta phi plus ... In this.
So if we now take the term we just found, U over V to the delta phi, and plug in the same machinery, we get back to 1. Right?
Yes.
Yes. So, like, is it more or less clear? So for one term we can find another one for free, but then
Exactly. Exactly. We have a symmetry. So we know a point, we use the symmetry, and we found the symmetric counterpart. That's the whole, I mean. But the most important point is that now we said, I erased it, sorry. We said that everything was found using the double discontinuity, in terms of the double discontinuity. this term with the double discontinuity, let's say roughly that is the limit v going to 0 of the GUV. This is very rough. The term that contains a v going to 0 limit is inside the symmetrized point, which is this point here, this part here. So, by starting with this assumption only, which is not even an assumption, it's a fact, we were able to find the double discontinuity of GUV. Actually, in this case, it's the full double discontinuity. So from this, we managed to find C delta L, which gives us all delta and A delta L for L greater or equal than 1. That's the logic. We started with this assumption. We went through our properties, and then using the relation that I showed you at the beginning, we managed to find the dimension and the delta L, which is exactly consistent to what we said yesterday. So yesterday we put unit operator in one hand, you use crossing symmetry on the other hand, and we saw that in addition of having the identity operator, we needed to have, now we didn't do the fully integral and so on because it's just horrible, and actually I don't think it's even possible to do it on the board, it would be too messy. But when you would do this exercise, you will find that this delta need exactly to be 2 delta phi plus 2n plus L.